This is section 8.1, the first day, and just a quick review here of our basic integration rules. There's 20 of them. We used them a lot in CalcAB. We're just going to highlight here the ones we use the most. So the most common ones are the constant multiple, antiderivative, bringing out the constant out front and multiplying it through at the end after we do the antiderivative. The sum and the difference rule, which is just that piece by piece antiderivative. Integrating one or a constant out here just gets you a linear. There's your reversal of your power rule. Here is your 1 over u. That's your u to the minus 1 power and the antiderivative of that. Of course, then we have e to the u, the antiderivative of that, and then changing the base to a. Changing the base to a puts that multiplier out here of 1 over the natural log of a. That's a little more obscure, so we're going to skip that. Sine, antiderivative of sine, of course, is really common. Same with antiderivative of cosine. And antiderivative of tangent is a little less common because we don't deal too much with this natural log. But we see it occasionally. It's not one of the most common though. But if we come over here to the other column, same with 11, not too common. Same with 12 and 13. But 14 gets to be a real common one you see because of the reversal of the derivative. Derivative of tangent is secant squared, so antiderivative then is a real common one to see. 15 and 16, well, 15 is not so common, but 16 is. It's that secant tangent pattern. And then the rest of them are not that common. So those are the ones that are starred here are the ones we see the most throughout the course. If we take a look at some antiderivative patterns that we're going to kind of be investigating, some we've done already, some we haven't. But you know, we can notice like number 1 and number 3 as u subs. So we'll get back into doing those u subs. Number 2 is actually a number 19. It's an inverse tangent, and we'll work with that a little bit this unit. This is a number 16. This is your secant tangent pattern for the antiderivative. We'll work with that a little bit. And then this is a number 20. That we see this occasionally from time to time. So we're going to kind of come up with some strategies here. Some we're going to revisit, like the u sub. Others we're going to learn for the first time. So when we talk about fitting into integrands, what we're talking about is we're looking for patterns in the integrand. Remember, the integrand is that stuff that's between the integration symbol and the differential. So we're looking for patterns in here to identify a particular strategy, like look for the derivative of a function for a u sub. So we're looking for those sort of patterns. We're also going to deal with expanding numerators. We're going to look at some completing the squares. We're going to look at actually long division. So we're going to look at some other things too in this unit. So for instance, we have this, and we haven't integrated anything like this before. But if we look at and we're actually going to learn to integrate this the long way later in this unit. But if we look at this pattern here, it matches up with a pattern that's number 19 in the front of your book with the reversal on the denominator here. So what we do is we recognize this pattern and we say, well, this has to be some sort of arctan answer. And so we start to match up then what the a means and what the u means. So for this one, what we're going to do is we're going to rework this to make it look more like this. So we're going to remove the 4, that constant can come up front. We're going to swap the terms on the bottom because they're separated by a plus sign, so that's mathematically equivalent. And we're going to write this first term in terms of a perfect square, the way we see it in 19. And then we can just identify the a and the u just by looking in that format. So we know that the a matches up with a 3 and the u matches up with an x. So now that we know that, we can match those up with the answer format. So we know we have a 4, and then we have a 1 over a, so that's going to be 1 over 3. And then we have a fraction out here, u over a, so that's, using these values, it's going to be an x over 3. So that is the antiderivative for this question. Now, if we take a look at this question and just change it a little bit, okay, I just multiplied the 4 and the 1/3 there, but we're going to change this in the next example just slightly. So instead of 4 over x squared plus 9, we're going to have 4x over x squared plus 9. Now the whole strategy changes. Instead of looking, this doesn't fit a pattern in the table, but it does fit a u sub pattern. So we see a derivative of this function. So we're going to go ahead and set up the u sub now. Because of the new pattern, we have a new strategy, or a different strategy. So we're going to set up our u sub, and we did u subs last year. So we're going to have to identify the higher power term as the u, and then we're going to have to differentiate that. So the derivative of u, du dx is 2x, and then we have to rearrange that. So we can solve for dx, that's du over 2x, and then we can put that into the integrand. So instead of this, we're going to put in our u. Instead of our dx, we're going to put in our du divided by 2x. We're going to do our canceling, and then we're going to go ahead and rewrite this. So we have a 2 left in the numerator. Now we have something much more simple to integrate. So we're going to pull the 2 out. We're going to rewrite this to make it look a little more obvious. If you want to stick to those 20 rules at the front of your book, we notice that this is one of those 20 rules. It's also just a natural log. We learned this as a natural log last year numerically. So this is 2 natural log of u plus c, and then we substitute back in to get it in terms of x. So this is 2 natural log of the quantity x squared plus 9 plus c. So just having a 4x term up here in the numerator instead of a 4 changes our strategy completely. The next one, and again, just a minor difference here. We started out with a 4, then we did one with a 4x, now we have a 4x squared. So a different look. This does not fit a pattern that's in the front of the book, so it's not going to fit one of your 20 integration patterns. It's not going to be a u sub because we don't have a function in its derivative. So what we have to recognize here is that we actually have a numerator that's bigger than the denominator. We know this because the powers match, but the coefficient in the numerator is bigger. And so whenever we have a number, whenever we have a numerator bigger than the denominator, we can divide it out using long division. It's kind of like if we had 13 over 7, we could say, well, how many times does 7 go into 13? And we can start doing the long division. So we're going to do the long division with polynomials. So we want to know how many times x squared plus 9 goes into 4x squared. So let's go ahead and look at that. So how many times does x squared go into 4x squared? So this polynomial is really 4x squared plus 0x plus 0. We're going to keep that in mind as we try to do this long division. So really it's a matter of looking at the highest power. So how many times does x squared go into 4x squared? Well, it goes in 4 times. And then we multiply, just like we do with long division. So we multiply 4 times x squared to get 4x squared, and 4 times 9 to get 36, and then we have to subtract that. So 4x squared minus 4x squared is 0. 0x minus 0x is 0x, and 0 minus 36 is negative 36. So this is our remainder. And we notice that the remainder has a lower power than the denominator. And once that happens, then we're done dividing. So this remainder looks like negative 36 over x squared plus 9. And so this we can integrate, because now we have this 4x squared over the quantity x squared plus 9 expressed as a whole number plus a remainder. And this remainder is less than 1 because the highest power up here is smaller than the highest power down here. And this also fits, this remainder also fits one of the patterns from the 20 rules in the front of your book. So we're going to go ahead and find the antiderivative of this. So we're going to split it up. We need the antiderivative of 4 and the antiderivative of this fraction. We know that the antiderivative of 4 is 4x. So we're going to get that in a second. The antiderivative of this is actually, again, a number 19. So we know we have an a of 3 and a u of x. So it's the same rule that we were working with a couple of examples ago. So we're going to factor out the 36, and we're going to set this up according to what our rule looks like. And then we can take the antiderivative of each. So the antiderivative of 4 is 4x. The antiderivative of here is going to be 36. And then we have to do 1 over a, so 1 over 3. Inverse tangent, or arctangent, means the same thing, of x over 3. Oops, that should be a 3. That's a typo. And then plus c. So simplifying this, then we have 4x minus 12 inverse tangent x over 3. Again, that should be a 3 plus c for that. So again, we changed the numerator so slightly, and we then had to come up with a different strategy to approach finding the antiderivative of that expression. There we go. There's the correct denominator now. So again, these should not be 5s, those should be 3s. So this last one is, again, the numerator is bigger than the denominator. So, this is kind of the new strategy for the day, is the long division. The other two strategies we've done before. So we're going to try the long division again. So we have, how many times does x minus 4 go into 2x? That's what this fraction is saying. How many times does the denominator go into the numerator? So x goes into 2x twice. So we're going to multiply by 2 up here. And then we're going to multiply that through. So that's 2x minus 8. Go ahead and subtract that. 2x minus 2x is 0. 0 minus a negative 8 is positive 8. Our remainder is lower power than our term in the denominator. So the remainder is 8 over x minus 4. And then we're going to go ahead and find the antiderivative of that. We're going to split it up like we did before. And we're going to treat it as 2 integrands. I removed the 8 from the second integrand. So finding the antiderivative of this is 2x. The antiderivative of this is 1 over, this 1 over x minus 4 is the natural log of x minus 4. The inside has a derivative of 1, so there's no chain rule needed. Then we have our plus c for our antiderivative. So this antiderivative, then 2x plus 8 times the natural log of x minus 4 plus c is the antiderivative for this problem here. So just in summary here, our essential question is, and our essential question is going to be the same pretty much throughout this unit. What strategies are we using to integrate more complicated expressions? So we have our 20 basic rules. We have our U sub. We did those last year. And then now we're starting to look at long division when we have a higher power in the numerator than we do in the denominator. So at this point, you can now go ahead and work on the first day homework for section 8.1 for that basic integration rules.